The next topic that we will cover are annuities. An annuity is a fixed amount of money paid or received at equal time periods for a fixed number of years. Usually, one would see an annuity as a retirement planning tool to provide a fixed cash flow for pensioners or retirees, but we are going to focus on annuity factors. An annuity factor is the sum of all the discount factors of every period and gives us an easier way of figuring out present values for regular cash flows. For example, if you will receive $1,000 per year paid annually for 5 years and use a discount rate of 5%, the annuity factor would be 4.3295, as the table on the right demonstrates. Hence, to calculate the PV quickly, you could simply multiply the annuity factor of 4.3295 by $1,000, which gives you a value of $4,329.50. While you can calculate the annuity factor by manually calculating each payment period and the corresponding discount factor, you would probably agree that it is quite onerous. Thankfully, someone has done all the calculations for us. If you search for annuity tables on the internet, you may find something that looks like the table in this slide. If we look for the row for 5 years on the left-hand side, and then go across the column under 5% interest rate per year, you can find the cumulative discount factor, or annuity factor, of 4.329, the same as we calculated in the slide earlier. Building upon our new knowledge of annuities, we can examine the concept of discounted cash flow, or DCF. DCF gives us a way of estimating the value of an investment based upon the expected future cash flows. For example, a company might be looking to invest in a new project and may want to see how much money it will bring in over the life of that project. Let's say that a plant built today is expected to earn $1 million per year for an expected life of 20 years and applying a discount rate of 5%. Using an annuity table, we can quickly find the annuity factor of 12.4622. Multiplying that factor by 1 million, we can see that the PV of the expected future cash flows from this project will be $12.462 million over 20 years. The next topic we will talk about is net present value, or NPV. NPV is defined as the present values of all future cash flows over the life of an investment, less the initial cost of the investment. And that is the subtle distinction between NPV and DCF. You need to calculate DCF in order to subtract the initial investment so that you can find the NPV. Let's explore that further by using an example. In this example, we are going to assume that our initial investment for business expansion will cost us $1,000. We expect that the expected life of this expansion to be 3 years, and each year this expansion will earn $400 for us. And finally, we are applying a discount rate of 5%, which includes our expectation of inflation and the opportunity cost of other investments. Using these variables, we calculate the discount factor for each of the cash flows and multiply that by $400 to get the PV of each cash flow. Then we sum the expected PVs and subtract that from the initial investment, which in this case gives us a positive NPV of $89.30. Many companies may look at the cost-benefit of a project by using the NPV decision rule. Projects with a positive NPV add value. They return enough cash to more than cover the cost of the project. Therefore, companies may choose to proceed with that project. Negative NPV destroys value. They fail to return enough cash to cover the cost of the project, and a company might choose to reject that. Now I will demonstrate how to calculate NPV and DCF using an Excel spreadsheet. Let's consider a hypothetical example where you need to invest $10 million today on a plant or a project that will return $1.75 million for the next 7 years. Let's assume the discount rate we use is 5% for this particular project. To model out the cash flows, we would do this on Excel. The cash flow from the first, or from time zero, is expected to be the minus value of the initial investment. And the cash flow starting in year one will be the positive amount of the cash flows. The discount value is simply defined as 1 plus the rate of interest, or the discount rate in this case, raised to the power of minus n. Filling in the columns, we can calculate the PV of each of the cash flows as the product of the cash flow multiplied by the discount factor for each of the years. The DCF is equal to the sum of all these values. The NPV of the project is the DCF, discounted cash flow, minus the initial investment, which in this case is positive $126,000 some odd dollars. Alternatively, we could use the formula for DCF to figure out the value of all the different cash flows, which is namely the cash flow of $1.75 million discounted by the cash flows at 5% for 7 years. And that would also give us the same value of 10.126153.45. Lastly, we will explore what happens when rates of interest change over the life of an investment. This may happen if you're looking at a bond with a step-up coupon, or perhaps a bank deposit that may have rates linked to rising inflation or future interest rates. Mathematically, one would compound interest at the old rate up to the date of the rate change and then use the new rate. For example, let's look at a principal amount of $100 that earns 5% per annum compounded annually, but rates step up to 7% at the end of year 3. In this slide, we look at the first interest payment of 5% paid at the end of year 1. We would compound that cash flow at 5% for years 2 and 3 and compound at 7% for years 4 and 5. Then for the interest payment in year 2, we would compound that at 5% for year 3 and 7% for years 4 and 5. If we continue this exercise for the interest payments from years 3 to the final interest payment in year 5, we can see that the total interest would be $32.54 and the total P plus I is $132.54. Again, this is a case that we don't see often, but it is important to understand the math so that we can compute the PV for this sort of cash flow.